So this is the 2015 Leaving Cert Higher Level Paper 2, and we're looking at question number 5. Part A says, prove that the tan of A plus B is equal to the tan of A plus tan of B all over 1 minus the tan of A times tan B. So this is an identity from your tables book. So I've taken a section from the tables book here. So it's this identity here down the bottom that we're trying to prove. So this proof, the easy way to remember this proof is to remember that in order to prove this, you need to use the two things above. So the two things above it in the tables book. So you should know that the tan of any angle, so the tan of an angle x, is the same as the sine of the angle over the cosine of the angle. So that's a very common trigonometric identity, should be learned off by heart. Tan of x is equal to sine x over cos x. So the tan of A plus B is therefore equal to the sine of that angle, A plus B, all over the cosine of the same angle, A plus B. And now you're able to use these two trig identities here to expand these out. So what we get then is the sin of A plus B is this one here. So in other words, I'm going to expand this on top here, and the cos of AB I'm going to do underneath there. So sin of AB is equal to the sin of A by the cos of B plus the cos of A by the sin of B. And that's all going to be over the green expansion here, which is cos A cos B minus sine A sine B. Okay, so now what we're going to do is, you can see now here that we've got the general shape of what we're trying to get to. We've got something plus something on top, something plus something on top, and something minus something on the denominator, the bottom, something minus something. So you're trying to get this to become this. So from here, the easy thing to remember here is that if you look at the simplest part of this here, you're trying to get the number 1 from this here. Because the bottom left-hand corner here is the bottom left-hand corner here. So how do you go from cos A cos B to 1? What would you have to do to the cos A cos B to get to 1? Well, the answer to that is divide cos A cos B by itself. So what we can do now is we can actually divide everything here by cos A cos B. So I'm going to do this over here now. So if I divide the top left corner, that's sine of A cos of B. If I divide that by cos A cos B, cos A cos B, then I divide this part here, the top right, so plus cos A sine B by the same thing, by the cos A cos B, and then divide this by itself, so cos A cos B divided by itself, cos A cos B. Then I'm just left with the bottom right. This is the negative here. The sine of A by the sine of B divided by cos of A by the cos of B. Okay, so again, just to be clear, I'm using this here, I'm dividing everything by that. You see here, everything gets divided by that, and this thing here on top was itself. So by doing that, what I end up with is the following. The cos b's here cancel. The cos a's here cancel. Cos a's and cos b's cancel here. And over here I have the cancels here. Yes, this stays as it is, nothing cancels here. Okay, so what does that give me then? Well, that gives me, up here on the top left then, I'm left with sine A over cos A. Now sine A over cos A is just tan A. That gives me tan A plus sine B over cos B, well that's just tan B. You can see now I'm beginning to get out what I was looking for. All over, everything here cancels with itself, leaving 1, minus sine A over cos A, well that's just tan A, and then sine B over cos B, that's just tan B, so it's tan A, tan B. So there we've proved the identity that we were asked, one from the tables book. Part B, find all the values of x for which the sine of 3x is equal to root 3 over 2. And x is between 0 and 360 degrees inclusive. So what we're going to do here is set your calculator to degrees mode. And if the sine of 3x is root 3 over 2, well that means that the angle, 3x, the sine of an angle is root 3 over 2. Well then the angle will be the inverse sine of root 3 over 2, the fraction. So that means then, if you do that in a calculator, the inverse sine of root 3 over 2 is 60 degrees. Make sure again your calculator is on degree mode. Okay, so 3x is 60 degrees. Now, if we think about the unit circle, we remember that we have ASTC, or cast, depending how you remember this, CAST. But sin, cos, and tan, they're all positive in here, sine in here, tan in there, and cos in there. So, because the angle is 60 degrees, that would be 60 degrees would be something like this. The other place that it would be, because it's positive 60, would be in here. So 60 degrees back from the 180. So it's 120 and 60. So 60 and then 120. So 60, 120 degrees. But then it's going to be, you can add 360 to each of these values as you go along. So if I add 360 for another full revolution. So if I add 360 to 60, I get 420 degrees. If I add 360 to 120, I get 480. If I add 360 to 420 again, I get 780. And if I add 360 to 480, I get 840 degrees. And you can keep going like this, but remember we're trying to solve for x. Now we only want the values of x between 0 and 360. So if 3x, if these are the values of the angle 3x, well x will be a third of each of these. So I'm going to divide everything here by 3. So x will be 60 divided by 3 is 20 degrees. 120 divided by 3 is 40 degrees. 420 divided by 3 is 140 degrees. Now we're only going to go as far as 360 or just below. 480 divided by 3 is 160 degrees. 780 divided by 3 is 260 degrees. 840 divided by 3 is 280 degrees. And we better go one more up here on top. So if I added 360 to 780, I would have got 360 added to that would be 1140. So that was another value up there that we could have got. 1140 degrees. And 1140 divided by 3 is 380 degrees. So that's gone beyond the 360 threshold. So there's all my values of x. 20, 40, 140, 160, 260 and 280. So they're all the values within the given domain. And that's the end of part B and the end of question 5.